Good morning, students. In the last session, we have discussed about dual nature of matter and radiation and Heisenberg uncertainty principle, and also we have derived de Broglie relation or de Broglie equation. So, in today's session, I will be discussing about hydrogen atom spectrum and quantum numbers and their significance. So let us begin today's class. First we'll see the hydrogen atom spectrum. Hydrogen atom spectrum. Here first we'll see the origin of the hydrogen atom spectrum. Here in the experiment we are taking a glass discharge tube. This is a glass discharge tube and it is connected to the power supply, and we are taking a slit and a suitable prism for the dispersion of the light and a photographic plate to collect the hydrogen atom spectrum. Here the hydrogen gas is taken in this discharge tube, that is glass discharge tube, and it is maintained at the low pressure of about 0.00 mm of mercury. Then a high voltage is applied across this discharge tube, ultimately across the gas which is taken in the discharge tube. We are applying a high voltage across this gas, that is hydrogen gas. Then the gas heats up. When the gas heats up, it glows. It glows is nothing but it emits light. The emitted light is made to pass through this slit. When we are applying the voltage across this hydrogen gas, it emits light. The emitted light is passed through this slit. Once the light passes through the slit, it is made to disperse through this prism. We are taking a prism. The light emitted by the gas is made to disperse through this prism, and various spectral lines. These are the various spectral lines which were dispersed on the photographic plate. Here we are collecting the various spectral lines on the photographic plate. So this is the hydrogen origin of the hydrogen atom spectrum. That is, we are getting large number of sharp lines. You can observe here on the photographic plate we are getting the various spectral lines. That is nothing but the hydrogen atom spectrum. We know that hydrogen atom contains only one electron. It contains only one electron, but in the spectrum, this is a spectrum you can see on the photographic plate. In the spectrum, we are observing a large number of lines. We can see large number of lines. So Bohr, he has given the reason why we are observing various spectral lines on the photographic plate. The reason is that a given sample of hydrogen contains large number of atoms. In the postulates, that is in the theories of atomic model, we studied that every element contains infinite number of atoms. We already know that every element contains infinite number of atoms. So Bohr has given the reason that here we are taking hydrogen sample, that is hydrogen gas as the sample. It is also a element which contains large number of atoms of the order of several millions. Suppose if we supply the energy to this gas sample, different atoms, we are telling that there are infinite number of atoms or large number of atoms. So different atoms will absorb different amount of energy. We are supplying energy to the gas atoms of hydrogen. So when we supply the energy, the different atoms will absorb different amount of energy, and they will excite to the different energy levels. We know that atoms will be absorbing different amount of energy. Once they absorb the energy, they will be exciting to the, or they will be excited to the different energy levels. according to the amount of energy absorbed. That is, how much amount of energy they will be absorbing. According to that, they will be jumping or exciting to the higher energy levels. For example, one atom is absorbing sufficient energy to shift their electron or to jump their electron maybe to the second energy level, or some atoms may absorb sufficient energy to shift their electrons to the fourth energy level, or some atoms may absorb sufficient energy or large amount of energy to excite their electrons to the infinity level. So in this way, the atoms may absorb different amount of energy and can excite the electrons to the various energy levels or various excited states. Once the electrons reach to the excited states, they will fall back or they will jump to the lower energy levels. Once they reach the excited energy levels, they tend to fall back almost immediately to one or the other lower energy levels. They will be falling back to the lower energy levels. The various possibilities by which the electrons fall back from various excited state energy levels to the lower energy levels is called as electronic transitions. You can see here in the diagram, once they reach the excited energy levels, these are the energy levels. You can see here we have given n is equal to 1, 2, 3. These are the different energy levels. Once the electrons excite to the higher energy levels, either it may be to third energy level or fourth energy level, or it may be to infinity energy level. Once they reach the excited energy levels, they immediately fall back to the lower energy levels. They immediately fall back to the lower, any of the lower energy levels, and the various possibilities by which these electrons fall back from various excited energy levels. These are the excited energy levels. Excited energy levels to the lower energy levels, that we are calling as electronic transitions. And during each transition, that is during each electronic transition, energy is released. That energy, the energy which is released, appears in the form of radiation. We are observing the energy released during the transition in the form of radiation. That radiation will be having specific frequency and specific wavelength. What we are telling, that is, there is a emission of radiation during each transition. Radiation is nothing but it is a energy released during transition, which appears in the form of a radiation, and that radiation will be having specific frequency and specific wavelength. This is about the origin of the hydrogen atom spectrum. Then we observe various spectral lines, that is various series of spectral lines in the spectrum of hydrogen atom, and they are Lyman series, Balmer series, Paschen series, Brackett series and Fund series. These are the 5 series of spectral lines which we are observing in the spectrum of hydrogen atom. So let us see one by one the series and how they are originated. First we'll see the Lyman series. Here the Lyman series are produced when the electron, see the diagram here, Lyman series is produced when the electrons jump from second, you can see here this is a second level, when the electron jumps from second, third or fourth or fifth or sixth or seventh or maybe from infinity level. That is, Lyman series is produced when the electron jump from any of the higher energy levels. Either it may be from second energy level, or it may be from third energy level, or from fourth energy level. or it may be from infinity energy level. That is, it is produced when the electron jump from, or when the electrons fall back from higher energy levels. Even it may be from infinity. Even it may be from infinity to the lower energy level, that is to the first energy level. This is a first energy level. We are observing Lyman series when the electron jump from higher energy level to the first energy level. That is called as a Lyman series. And the frequencies of various spectral lines. You can see here, these are the spectral lines, and the frequencies of these various spectral lines of the series can be obtained by substituting n1 is equal to 1 and n2 is equal to 2 or 3 or 4 or etc. In the equation, nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. We are getting the frequencies of various spectral lines by substituting n1 is equal to 1 and n2 is equal to 2, 3, 4, etc. In the equation, nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. And these spectral lines, or these series of lines, are observed in the ultraviolet region. That is, we can find this series of lines in the ultraviolet region of the electromagnetic spectrum. So this is about Lyman series. Next we'll move to Balmer series. Second series is a Balmer series. Here Balmer series is produced, or it results when the electron jump from, here when the electron jump from either from third, fourth, fifth, or even it may be from infinity level to the second energy level. This is the first energy level. This is the second energy level. Balmer series is observed, or it results when the electron jump from higher energy level, or even it may be from infinity level to the second energy level. This is a second energy level. And the frequencies of various spectral lines in the Balmer series can be obtained by substituting n1 is equal to 2 and n2 is equal to 3 or 4 or 5, 6, etc. in the same equation, that is in the nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. And these lines, that is spectral lines in the Balmer series, are found in the visible region. We can observe these lines, spectral lines in the visible region. And third series is a Paschen series. Here it originates, or it produces when the electron jump from higher energy levels to the third energy level. When they fall back from higher energy level to the third energy level, that time we are observing the Paschen series. And the frequencies of various spectral lines in the series can be obtained by substituting n1 is equal to 3 and n2 is equal to 4, 5, 6, etc. in the equation, that is nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. And the lines, that is spectral lines in the Paschen series, are found in the infrared region. We can observe these lines in the infrared region. And the fourth type of series is a bracket series. Here we are observing, or we can found the bracket series when the electron jump from fifth, sixth, seventh or infinity energy level to the fourth energy level. When the electron jump from either fifth, sixth or seventh, or from infinity level to the fourth energy level, that time we are observing the bracket series. And the spectral lines, frequencies of these spectral lines can be obtained by substituting n1 is equal to 4 and n2 is equal to 5, 6, 7, etc. in the equation, that is nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. And these spectral lines in the bracket series are found in the infrared region, that is in the far infrared region. We can observe these spectral lines in the far infrared region. And the last series is a fun series. Here the fun series originates, or it results when the electron jump from fifth or sixth or from any of the energy level, or even from the infinity level to the fifth energy level. This is the fifth energy level. Fun series is observed when the electron jump from either sixth, seventh or infinity level to the fifth energy level. And the frequencies of these spectral lines can be obtained by substituting n1 is equal to 5. You can observe here, this is the lower energy level, or it is a fifth energy level. Here n1 is equal to 5, we have to substitute, and n2 is equal to 6 or 7 or 8 or infinity, that is etc. in the equation. Nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. By substituting n1 is equal to 5 and n2 is equal to 6, 7, etc. in the nu bar equation, that is nu bar is equal to RH into 1 divided by n1 square minus 1 divided by n2 square. And this is about a hydrogen atom spectrum. First we have seen the origin of the hydrogen atom spectrum, and next that is various series in the hydrogen atom spectrum. Next we'll move to the quantum numbers. Here the quantum numbers are the numbers which identify the state of an electron and which specify the energy associated with it and the distance between the nucleus and the electron, that we are calling as a quantum numbers. Quantum numbers are nothing but the numbers which helps us to identify or determine the state of an electron and which also specify the energy associated with the electron, and also we can determine or measure the distance between the nucleus and electron. Those numbers are called as a quantum numbers. And each electron in an atom is associated with 4 quantum numbers, and those are, the 4 quantum numbers are principal quantum number, azimuthal quantum number, magnetic quantum number, and last one is a spin quantum number. These are the 4 quantum numbers which we have to study. First one is a principal, or it is also called as a radial quantum number. First quantum number is a principal or radial quantum number, and it is denoted by the letter n. It determines the energy of an electron to a large extent. Using principal quantum number, we can determine the energy of the electron. And it also determines an average distance of an electron from the nucleus. We know that electron will be moving around the nucleus and outside the nucleus. So this principal quantum number helps us to determine the average distance of the electron from the nucleus. That is the distance between the nucleus and the electron can be calculated or determined by using principal quantum number. As the value of n increases, energy of an electron also increases and the electron gets farther away from the nucleus. As we go on increasing the value of n, or when the value of n increases, that is principal quantum number increases, at the same time, the energy of the electron also increases and the electron will move farther away from the nucleus. And the principal quantum number n have the integral value from 1 to infinity. So thus we have n is equal to 1, 2, 3, 4 and so on. And the shells here we are having are k, l, m, n, etc. And the maximum number of electrons in each shell will be 2n square. We have to calculate the maximum number of electrons in each shell by using 2n square formula. So this is a principal quantum number. Next we have is a azimuthal quantum number, or it is also called as a angular momentum or subsidiary quantum number, and it is denoted by letter L. So here it is called as a azimuthal quantum number or also angular momentum quantum number or subsidiary quantum number, and it is denoted by the letter L, that is small letter L. Here the azimuthal quantum number determines the angular momentum of an electron and also the shape of atomic orbital. We can determine the angular momentum as well as the shape of the atomic orbital. The number of such shells are indicated by the number that is azimuthal quantum number. We can determine the shells and which are indicated by the azimuthal quantum number, and L can have the values from 0 to n minus 1. It can have the values between 0 to n minus 1 for given value of n, that is principal quantum number. If n is equal to 1, then L will be equal to 0 and there will be a possibility of only one orbital. That is, when n is equal to 1, L is equal to 0, only one orbital is possible, that is s orbital. If n is equal to 2, then L will be equal to 1 and two orbitals are possible. See here we have to substitute the value of n here, n minus L. We have to substitute here in the equation or in the formula n minus L. For example, if n is equal to 1, we are substituting n is equal to 1, then 1 minus 1 will be 0. And if we are substituting n is equal to 2, then 2 minus 1 will be 1. That is L will be equal to 1. If we are substituting n is equal to 3, then 3 minus 1 will be equal to 2. That is L is equal to 2. If we substitute n is equal to 4, then 4 minus 1 will be 3. L will be equal to 3. So if n is equal to 1, then L will be equal to 0. See here we have to substitute the n value here. 1 minus 1 will be 0. So L will be equal to 0. And only one orbital will be possible, that is s orbital. If we substitute n is equal to 2, then L will be equal to 1. Two orbitals are possible. Those are s and p orbital. If n is equal to 3, then L will be equal to 2 and 3 orbitals will be possible. Those are SPD. SPD orbitals are possible, 3 orbitals. If n is equal to 4, then L will be equal to 3 and 4 orbitals are possible. Those are S, P, D and F. These are the 4 possible orbitals. And the next one is a magnetic orbital quantum number. It is represented by ML. M with, that is, M is a small letter and L you have to write as a subscript. Magnetic orbital quantum number is represented by ML. The magnetic orbital quantum number, it gives the spatial arrangement or orientation of atomic orbitals in the magnetic field. It helps us to determine the arrangement or orientation of the atomic orbitals in the presence of the magnetic field. For a given value of azimuthal quantum number, the magnetic orbital quantum number can have the integral values from -1 to +1 including 0. That is, for given azimuthal quantum number, the magnetic orbital quantum number will have the values from -1 to +1 along with 0. When L is equal to 0, then ML will be equal to 1 and S subshell and only one orientation is possible. That is atomic orbital orientation. We are telling the orbital orientation here. If L is equal to 1, then ML is equal to 3. The values will be -1, 0 and +1. And P subshell and 3 orientations will be possible. There will be 3 orientations in the P subshell. If L is equal to 2, ML will be equal to 5 and the integral values may be -2, -1, 0, +1, +2 and D subshell with the 5 orientations are possible. If L is equal to 3, then ML will be equal to 7 and the integral values may be -3, -2, -1, 0, +1, +2, +3 and possible subshell is a F subshell with 7 orientations. This is about a magnetic quantum number. And the last is a spin quantum number. Here the spin quantum number is represented by ms, small letter m with a subscript s. The electron moving around the nucleus spins about its axis and the spin may be in clockwise direction or in the anti-clockwise direction. Here we know that in the atomic theories only we understood that there will be a nucleus at the center of the atom and electrons will be moving around the nucleus. And these moving electrons will be having their own spin. They will be having their own spin and nucleus will be spinning about its own axis. And this electron spin may be either in the clockwise direction or it may be in the anti-clockwise direction. That is, electron will be moving around the nucleus but with a spin. And that spin of the electron, either it may be in the anti-clockwise direction or it may be in the clockwise direction. And the spin quantum number may have two values, that is plus half and minus half. We know that there are two types of spins, that is clockwise spin and anti-clockwise spin. That is, the electron may spin in both the directions and the spin quantum number can have, accordingly it can have two values, that is plus half and minus half. And this is symbolically represented as a arrowhead above and arrowhead below. Each orbital can have a subshell and it holds two electrons of opposite spin. That is, for example, if I am taking one s orbital, it can hold or it can have only two electrons of opposite spin. If the two electron having sign of same spin, then they are said to be having parallel spin. If the two electron have same sign spin, if they have a sign of a same spin, then we are telling those electrons as having a parallel spin. They have a parallel spin. While those having opposite spin, if they have a opposite spin, then they are said to be anti-parallel spin. If they have sign of same spin, then we call as a parallel spin. If they have opposite spin, then we are telling them as an anti-parallel spin. Next, we'll see the significance of quantum numbers. Principal quantum number, that is n, determines the energy of the electron, and it also determines the average distance of the electron from the nucleus. That is, we can determine the energy of the electron as well as the distance between the average distance between the nucleus and the electron. Azimuthal quantum number determines the angular momentum of the electron, and it also determines the shape of the atomic orbital. Using the azimuthal quantum number, we can determine the angular momentum of the electron and the shape of various atomic orbitals. Magnetic orbital quantum number gives the spatial arrangement of atomic orbitals or orientation of the atomic orbitals in the magnetic field. Using magnetic orbital quantum number, we can determine or we can tell the orientation of the atomic orbital in the presence of the magnetic field. And the fourth significance is spin quantum number determines the spin of the electron. That is, it tells whether the electron have the parallel spin or anti-parallel spin. So this is all about today's class. Here in the today's class, we have discussed or we have studied about a hydrogen atom spectrum, that is origin of hydrogen atom spectrum and various series in the hydrogen atom spectrum. Next, we studied about the quantum numbers, four quantum numbers, that is principal quantum number, magnetic quantum number, azimuthal quantum number, and spin quantum number. Lastly, we have studied the significance of quantum numbers. So this was all about today's class. Here I will be wound up in the class. Thank you.